This is video 22 of the thermal part with Lars-Erik, and it is about DewPoint and BubblePoint calculations. I will go through the algorithms that are also presented in figure 14.1 to 14.4 in the textbook. That is in block diagrams. I will just write the procedures. I start with presenting the variables and the equations. And I start with stating that the fugacity coefficient is a function of temperature, pressure, and the vapor composition. And the activity coefficient is a function of the temperature and the liquid composition. And the saturation pressures is a function of temperature for each component. Then we make use of the extended Raoult's law, and for yi, that is xi times the activity coefficient times the saturation pressure divided by the fugacity coefficient times the pressure. This is 48, and for the x, this is y times the fugacity coefficient times the pressure divided by the activity coefficient times the saturation pressure. That is 14.9. Then we have the sums of this, so that the sums of y's equal to 1, and the sums of x's should be equal to 1. Explicitly expressed by the pressure, if we take these expressions for the y's and for the x's and express them by pressure, then we can write this as the pressure is the sum of xi times gamma times the saturation pressure divided by the fugacity coefficient. This is equation 1410. And the last one is a similar equation with the sums of 1 divided by y times the fugacity coefficient divided by the activity coefficient and the saturation pressure for each component. And this explicit expression of the extended Raoult's law is equation 1411. And then I will use these equations for this bubble and dew calculation. And the first one is the bubble P calculation. And it is given in figure 14.1. Then we start to specify the temperature and the liquid composition. Then we start with setting all the initial fugacity coefficients to 1. Then we calculate the saturation pressure as a function of temperature. We assume that we have an equation for the saturation pressure for each component, and when we know the temperature, we can calculate these saturation pressures. Then we calculate the activity coefficients as a function of temperature and the liquid compositions. We assume that the activity coefficients are functions of temperature and the liquid composition. Then we calculate the pressure from 1410. We have this equation which is based on the extended Raoult's law, which states that it is the sum of the mole fraction in liquid times activity coefficient times saturation pressure divided by the fugacity coefficient. And we have now given an initial fugacity coefficient, so we can calculate this equation 1410. Then we calculate the yi, or all the yi's from 14.8. When we know the pressure, and then we can calculate the vapor composition from this equation. Then we can calculate the fugacities as a function of temperature, pressure, and the vapor composition. We assume that the fugacity coefficient is a function of temperature, pressure, and the vapor composition. And then we recalculate the pressure from 1410. We have got a new fugacity coefficient, so we recalculate that equation. And then one way to iterate is to ask whether the pressure has changed. More than some tolerance. And if not, that is okay. And if there has been a change, then we recalculate the y's, and then we can refine the fugacity coefficient so that we get a more accurate answer. But this bubble P calculation is a quite straightforward calculation. Then we go on to the DewPoint calculation. This is given in figure 14.2. A DewPoint calculation starts with specifying the temperature and the vapor composition. Then we calculate the saturation pressures for all the components. We again assume that the saturation pressures are a function of temperature. Then we define initial fugacity coefficients and initial activity coefficients, and for a start we set that to 1. Then we calculate the pressure from equation 1411. The pressure is the sum of 1 over y times the fugacity coefficient divided by the activity coefficient and the saturation pressure. That is, this equation is a consequence of a combination of an extended Raoult's law and a summation equation. But we have so far assumed that the fugacity coefficients and the activity coefficients are 1. Then we calculate all the fugacity coefficients. They can be calculated when the temperature, pressure, and the vapor compositions are known. Then we calculate the liquid compositions. They can be calculated by this equation 14.9. Then we normalize all the x's by setting the new x's equal to xi times 1 over the sums of xi's. The reason why we have to normalize the x's, or there are other ways to do this, but the problem with calculating the x's from this equation is that we cannot be sure that the sum of these x's are actually 1. That is not implicit in that equation. So, to make sure that the sum of these x's are actually 1, we say that the new x's are normalized by taking the new x as the old x divided by the sum of all the old x's. Then we calculate all the activity coefficients, and then we can ask, has any of these activity coefficients changed more than some tolerance? If not, calculate the pressure from 1411. If it has changed, then we have to go back and recalculate the x's. If not, we calculate the pressure by this equation, now with updated fugacity coefficients and activity coefficients. And then we also have to check whether this pressure has changed and more than some tolerance. And if it has, then we have to calculate all the fugacities again. So we have one inner loop here and one outer loop. But if not, then this should be okay. Then all the calculated values should be justify these equations. So we see that the bubble P is a quite straightforward calculation, and DewP is a more complex calculation, and the reason is that we actually do not know the fugacity coefficients and the activity coefficients, and it has to be a part of some iteration. Then we go to a bubble T calculation, and this is not exactly the same as in figure 14.3, and because what I do is that I perform a guess of the initial temperature in the figure 14.3. It makes some method for estimating the initial temperature, I just start with a guess. The procedure starts with specifying the pressure and the excess, and to set the fugacity coefficients initially to 1. And then we guess initial temperature. Then we calculate saturation pressure, because when we know the temperature, we can calculate the saturation pressure. And we can calculate the activity coefficients. When we know the temperature and the liquid composition, we can calculate the activity coefficients. We can calculate the Y's from 14.8. This we can then calculate the fugacity coefficients, and we can check if the sum of Y's is equal to 0. If yes, everything is okay. If not, then we have to guess a new temperature. So this, it can be discussed whether it is better to have the calculation of the fugacity outside, but that is, we might have that statement outside. That is a way to normalize the Y's. We could have a normalizing of the Y's inside here, but here we have the check of the sum of Y's at the end. Then we have one last example, which is a DewT calculation. Again, it is approximately the same as in figure 14.4, but the principle here is by guessing at the initial temperature, or actually guessing the temperatures also after the procedure. The procedure starts with specifying the pressure and the mole fractions in the vapor, set the fugacity coefficients initial to 1 and the activity coefficients initially to 1. And then we guess temperature, or we actually guess, not the initial, we guess the temperature, then we calculate the saturation pressure as a function of temperature. We calculate the fugacity coefficient as a function of pressure, temperature, and the vice. And we then calculate the x's from equation 49, when we know both the fugacity coefficient and the activity coefficient, then we can calculate the x's. Then we normalize the x's. The new x's equals the old divided by the sum of all the x's. Then we calculate the activity coefficients as a function of temperature and the liquid composition. And if this activity coefficient has changed, then we have to recalculate the x's. And then if the sum of x's is 1, then that is okay. But if not, we have to go all the way back and guess a new temperature. And what I have done is that I have presented some working equations, which is based on an extended Raoult's law, and I have shown the principles for these 4 types of bubble and dew point calculations: bubble P, dew P, bubble T, and dew T. And I have also tried to show that the bubble P calculation is the simplest, and then we have increasing complexity of these calculations. So this is the end of video 22. This is video 21 in the thermal course with Lars-Erik. It is about development, this equation based on a flash situation. The flash situation is that we have a feed with a known composition. The sets are the fractions, F is the total feed. Then we have a flash with a pressure and a temperature, and we have a vapor with a vapor composition with the vice, and we have a liquid with the liquid composition, the x's. And we assume that it is equilibrium between the vapor phase and the liquid phase. And then we start with material balances. The feed equals L plus V. We assume that it is steady state. This can be written that 1 equals L over F plus V over F. And then we have a component material balance. This equation states that the amount of component I in the feed equals the fraction of component I in the liquid times the liquid flow plus the fraction of the vapor of component I times the amount in the vapor flow. Then set I equals xi times L over F plus y times V over F. I just divide it by F. And set I is yi over k. Ki is yi over x. That is what is meant by k. I just manipulate this equation. And we get a revised expression for the set. And then the reason why we did this manipulation is that now set is expressed by the y, and else there are the k values and the v over f ratio. And then the y can be expressed by set over 1 over k plus 1 minus 1 over k I v over f, or y I equals to set I times k I divided by 1 plus k I minus 1 times the v over f ratio. And this is equation 1016. And we have a similar equation for the x's. x. So we easily convert this to an equation for the x's. For some reason in the textbook they have developed this first equation for the y's in chapter 10, and then we add one more equation here in chapter 14 when we are calculating the different conditions, but this is the equation 14. 16, and then we go further, and then I put up a question: why using a function which is the sum of y's minus the sum of x's equal to 0 as an iteration variable. The topic is that we use this function, the sum of y's and the sum of x's equal to 0, as an iteration variable. We can refer to figure 14.5 in the textbook. We can make an fy expression which is the sum of all i's of set I ai divided by 1 plus v over f times ki minus 1 minus 1. This is the sum of all the y's minus 1, that should be 0. And similarly, we can put up an equation for the sum of all the x's, which in this case is expressed by 14.16. And since that sum should be 1, we can subtract 1 and say that that should be equal to 0. Or we do not need to state that either. We can just say that fy is this sum minus 1 and fx is that sum minus 1. And a general solution procedure is that f is fy minus fx, or the sum of sets I ki minus 1 over 1 plus v over f ki minus 1. should be equal to 0. This is 1490. And this is the Rashford-Rice equation. From 1952. And this is efficient because df over d over v over f is always negative. Or f of v over f is a monotonic function. That is, if we change the vapor to feed ratio, then we know that this function is a monotonic function, so that we will always get a solution to this. We can vary this, and we can be sure that we will get a solution to this. And what is perhaps more important than efficient is that it is robust, which means that we will always get a solution. And the procedure guess v over f, and calculate f if f is 0, then calculate the vapor, liquid, the whites, and the excess. Else, try a new v over f. That is a efficient and robust calculation procedure to calculate a PT flash. Then one more comment is that in modern process simulation tools like Aspen HYSYS, more efficient algorithms using extra variables. Are used, and one example is this inside out algorithms. So here first we have developed working equations for the liquid fractions and the vapor fractions, and then it is shown that these can be used in a method for calculating a function based on the vapor to feed ratio that is monotonic, that is, it is easy to solve, and then that is a reasonable basis for a procedure by guessing and iterating on the vapor to feed ratio, and this can be used in algorithms, but in modern process simulations programs like Aspen HYSYS, they have even more efficient algorithms, adding extra variables for iteration. But this is meant to give an idea of how this can be calculated in a computer. So this ends video 21. This is video 21 in the thermal course with Lars-Erik. It is about development this equation based on a flash situation. The flash situation is that we have a feed with a known composition. The sets are the fractions, F is the total feed. Then we have a flash with a pressure and a temperature, and we have a vapor with a vapor composition with the Y's, and we have a liquid with the liquid composition, the X's. And we assume that it is equilibrium between the vapor phase and the liquid phase. And then we start with material balances. The feed equals L plus V. We assume that it is steady state. This can be written that 1 equals L over F plus V over F. And then we have a component material balance. This equation states that the amount of component I in the feed equals the fraction of component I in the liquid times the liquid flow plus the fraction of the vapor of component I times the amount in the vapor flow. Then set I equals xi times L over F plus y times V over F. I just divide it by f, and set I is yi over k. Ki is yi over xi. That is what is meant by k. I just manipulate this equation. And we get a revised expression for the set. And then the reason why we did this manipulation is that now set is expressed by the y, and else there are the k values and the e over f ratio, and then the y can be expressed by set over 1 over k plus 1 minus 1 over k I e over f, or y I equals to set I times k I divided by 1 plus k I minus 1 times v over f ratio, and this is equation 1016, and we have a similar equation for the x's. K is y over x, so we easily convert this to an equation for the x's. For some reason in the textbook they have developed this first equation for the y's in chapter 10, and then we add one more equation here in chapter 14 when we are calculating the different conditions, but this is the equation 14. 16, and then we go further, and then I put up a question, why using a function which is the sum of y's minus the sum of x's equal to 0 as an iteration variable. The topic is that we use this function, the sum of y's and the sum of x's equal to 0, as an iteration variable. We can refer to figure 14.5 in the textbook. We can make an fy expression, which is the sum of all i's of set I ai divided by 1 plus v over f times ki minus 1 minus 1. This is the sum of all the y's minus 1. That should be 0. And similarly, we can put up an equation for the sum of all the x's, which in this case is expressed by 14.16. And since that sum should be 1, we can subtract 1 and say that that should be equal to 0. Or we do not need to state that either. We can just say that fy is this sum minus 1 and fx is that sum minus 1. And a general solution procedure is that f is fy minus fx, or the sum of sets I ki minus 1 over 1 plus v over f ki minus 1 should be equal to 0. This is 14.90. And this is the Rashford-Rice equation. From 1952. And this is efficient coefficient because df over d over b over f is always negative, or f of v over f is a monotonic function. That is, if we change the vapor to feed ratio, then we know that this function is a monotonic function, so that we will always get a solution to this. We can vary this, and we can be sure that we will get a solution to this. And what is perhaps more important than efficient is that it is robust, which means that we will always get a solution. And the procedure guess v over f, and calculate f if f is 0, then calculate the vapor, liquid, the whites, and the excess. Else, try a new v over f. That is a efficient and robust calculation procedure to calculate a PT flash. Then one more comment is that in modern process simulation tools like Aspen HYSYS, more efficient algorithms using extra variables are used, and one example is this inside out algorithms. So here first we have developed working equations for the liquid fractions and the vapor fractions, and then it is shown that these can be used in a method for calculating a function based on the vapor to feed ratio that is monotonic, that is, it is easy to solve, and then that is a reasonable basis for a procedure by guessing and iterating on the vapor to feed ratio. This can be used in algorithms, but in modern process simulations programs like Aspen HYSYS, they have even more efficient algorithms, adding extra variables for iteration. This is meant to give an idea of how this can be calculated in a computer. So this ends video 21.